Hey class, this is Mr. Hofstad with the third and final example from our 7th lesson on friction in Unit 3. So we're working with some two-dimensional vectors here, two-dimensional forces, very similar to the first lesson of this unit, but now we're throwing in friction to the mix. So the question wants us to determine acceleration of this box, and it gives us the coefficient of kinetic friction, right? And we know we need to be using kinetic friction because we have a moving box, right? As soon as the box is accelerating or has any motion, we're using our coefficient of kinetic friction, or mu k, which is in this example 0.93. So the higher this coefficient of friction, the stickier it is, right? So this is quite a rough block and surface that it's sliding on, which means it has a high mu k. So this question is a little bit weird. It does break some of the rules of physics, so not a super likely question to get on an exam, and you'll see why when we get to the end of it. So we are given this 190-degree force acting diagonally on the block, so it's pushing it into the surface even harder, right? And it's also pushing it forward and to the right. So we need to find all the components of this force F, right? Once we have those components and we know we have gravity and our normal force, right? We're going to use Newton's first law in our vertical or in our y direction, and Newton's second law, right? Unbalanced forces in this horizontal direction, because our box is actually sliding and accelerating, and that's the value we want to determine, right? So first we want to find or break F into components. So Fx, we know we have 24 degrees. Fx is our adjacent side. Hypotenuse is 190. So to find Fx, we're going to use adjacent hypotenuse, which is our cosine of our 24 degrees, which is equal to Fx over 190. Fx is equal to 190 cosine of 24 degrees. I'll leave that in my calculator so that I don't have to worry about storing numbers. Just another way to do it. If you were to actually solve that right at this step and store it in your calculator, that's just as good. I'll just give you a new, different way to do it. So Fy is our opposite side over hypotenuse, so we're going to be using sine 24 degrees is equal to our y component over 190. So very similar to our Fx, we have 190, but now we have sine of 24 degrees. Okay, and both of those, sorry, according to my reference system, right is positive, so this would be positive, and according to my reference system, this is negative. All right, so I have the components of this 190-degree force applied diagonally. Now I can do my vertical and horizontal analysis. So in the vertical, since it's sitting on a surface, we know that acceleration equals 0, so we're going to use our Newton's first law, our principle of physics, 0. So F net, since acceleration is 0, needs to equal 0, where the net force has two forces acting down, one force acting up. So our only force acting up is Fn, and acting down we have our Fy and our Fg, force of gravity. This 18.5 kilogram block, assuming it's on Earth, will experience force of gravity of its mass times gravity. So I'm going to rearrange this formula by adding Fy and Fg to the other side. So here we have Fn which is our unknown, is equal to Fy. I'll just put in the value for Fy here. We've got 190 sine of 24. Nope, don't worry about the negative. I included that in the general form here. I said it was going down, so this is 190 sine 24 going down. And likewise, our Fg was negative here, right? So I'm going to add it, and it's going to be a positive mass times acceleration. 18.5, 9.81. So my normal force comes out as 258.8 newtons, and that would be up. All right, I have Fn. Now I'm able to solve for my force of friction. Force of friction, which is always equal to our coefficient of friction, in this case kinetic because we're moving, times the normal force. So we have 0.93 times 258.8 newtons, coming out as 240.65 newtons. So last step, we're going to balance our horizontal. We know we're working with unbalanced forces, so it's a principle of physics 1, Newton's second law. So our force is equal to our mass times our acceleration. Right? That would be our net force. So let's look at all the forces we have going on in this horizontal direction. We have our x component of this 190-degree external force, right, Fx. And we also have the force of friction resisting it, which I forgot to draw on, but that was important here. So it's going to be Fx minus force of friction is equal to the mass of the block, right? That's our net force, mass times our acceleration, which is what we're looking for. Okay, so we're going to solve for acceleration in this equation by dividing both sides by mass. Acceleration is equal to our Fx, which was 190 cos 24, minus the force of friction, which we just determined as 240.65. And we're dividing it by the mass of our object, 18.5 kilograms. And this gives us a negative number, which is why right off the bat I told you this was an unrealistic example. 36.3 meters per second squared, or 3.63 meters per second squared left. So this is some magic box that as I'm pushing it forward, it's actually accelerating backwards because the friction is so strong. So this wouldn't occur in real life, just showing you the math behind it. What would really happen here is the box just wouldn't move. So if you get weird questions like that, just work on them till they're finished, right? And maybe make a little note that this is not realistic, right? Something can't accelerate backwards. You can't have a force of friction greater than the applied force, right? That's a non-real example, right? Talk to you guys shortly for our 8th and final lesson.